Hello students, welcome to another video of metric space. Today we will discuss the definition and one theorem on the open set. So first of all, the definition of open subset. Definition of open subset. Definition of open set or open subset. In the previous lecture, we have seen the definition of open sphere. SR of X is said to be open sphere if for each y belongs to that SR of X, distance of that center X and Y is less than R. And now today we will discuss the open set. Now open set, a subset suppose U, a subset U of metric space XD, metric space XD is said to be open, that is open set, or D open. Generally we will use the notation set subset U of metric space is said to be open set. We will use the word open set or notation open set. You may call it as D open because D open means function D is applied on set X, so XD is metric space. So a subset U of metric space XD is said to be open if for each, underline the word each, if for each X belongs to U, for each X belongs to this set U, there exists any radius which is greater than 0, any R greater than 0, that is there must be at least one R greater than 0 such that SR of X, that is if you take any element X belongs to U, so there must exist a radius R greater than 0 such that open sphere centered at X with that radius R must totally contain in U, Suppose now this is the theoretical definition. A subset U of metric space XD is said to be open whenever for each, this is the most important word, because we have, if we say this U is open, then each and every element of this X, for each and every element of X, if we draw the open sphere centered at every element of U, if we draw the open sphere on, that is if you draw the open sphere centered at any element of U, then that open sphere must totally lie in that set U. This is the definition of open set. Suppose this is metric space XD, then we say that suppose this is set U, then we say that this set U is open. Whenever we say that this set is U is open, when for any X belongs to this set, if we take suppose this X or suppose this another X, suppose this X, any X, for every element in that set U, if we, there must be some R greater than 0 such that SR of X is totally contained in U. So if we consider this set U except the boundary points, then we can draw any radius. Suppose this point X, then we can take a radius R is equal suppose 0.0001, then suppose this is radius and we can draw this open sphere and which is totally contained in this set. That is, again suppose this is X, then we can find any radius and this open sphere contained in U. That is, for any X, for each and every element of this set U, there must be some R greater than 0, such that after taking this radius and draw the open sphere, then that open sphere must contain in that set, the radius must be greater than 0, so it may be 0.00001. If we take this X which is very close to this boundary, then the distance between this boundary and this X, that is very less distance, but if we consider that distance and draw the open sphere, then that open sphere totally contained in U, so we can say that U is open subset of metric space XD. This U is said to be open subset of metric space XD if for every element of that set, if we draw the open sphere centered at any element, then that open sphere must be totally contained in U, then we can say that this U is open. So suppose if we take this element on the boundary, suppose this element on boundary, then we cannot find any r greater than 0. If you find this smallest radius possible, then that open sphere goes exterior to this u, then this boundary point must be does not belongs to. If u contains its boundary point, then this u cannot be a open set. I think you are getting this now. So whenever you or you said, we can say that this u is open set then when our u contains its interior points, not the boundary points. If u contains its boundary point, then we cannot find any radius greater than 0 such that that open sphere centered at this x and with any radius which does not belongs to this u. We have to find any radius r greater than 0 such that SR of x must contain in u. For the boundary point, it is not possible to find the radius such that that open sphere contained in u. So our open set must contain its interior points, not the boundary and exterior points, only the interior points. This is the definition of open set. Now we will take one note. Any metric space X is itself a open set. Any metric space X is itself a itself an open set. Suppose this is XD be a metric space. Then for every element of this set X, we can find radius r greater than 0 such that SR of x contain in metric space, which because we are seeing all these terms in metric space, and for every element of that metric space and we draw the open sphere, in that that open sphere must totally goes in that metric space. So metric space is also open set. Similarly also the phi, that is the empty set, is also a open set in any metric space. Also phi is open set in any metric space, XD, because phi is empty set, and for empty set there is no element on which we can draw the open sphere, and that open sphere must contain in that set. So there is no element, so the condition of open set is obviously satisfied, and phi is also a open set. Now we will take one theorem. This is the important result. This theorem can be asked for 4 marks. Let the statement of the theorem is, let XD be a metric space. XD be a metric space. Let x belongs to x and r greater than 0. X belongs to x, that is x is any element of non-empty set x and r is radius. Then the open sphere SR of x is open set. XD be a metric space, x belongs to x be any element and r greater than 0 such that then the open sphere. So this theorem can be asked in another way as, show that or prove that every open sphere is open set. Every open sphere is open set. This is the another statement of this theorem, or this statement can be asked as example such that prove that or show that this every open sphere is open set. So we have to show that every open sphere is open set. We have given that XD be a metric space, given that XD capital X be a metric space and x belongs to x and r greater than 0. Also we have given that this SR of x is open set. Sorry, we have given that SR of x is open sphere, and we have to prove that this SR of x is open set. SR of x is open sphere. SR of x is open sphere, and our claim is SR of x is open set. is an open set. To prove that this SR of X is open set, we have to use this definition. That is, we have to prove that for every element in that open set, a subset U of metric space is said to be open if for each X belongs to U. That is, for every element of that set U, there must be some radius greater than 0, such that SR of X centered at that X must belongs to this set U, must goes to this set U. That is, U must contain that open sphere. So we have now we have to prove that this SR of X is open set. So we have to prove that each and every element in this open sphere, for each and every element of this open sphere, there must be some radius such that that open sphere centered at that point in this open set, sorry, in this open sphere must contain in SR of X. So we have, suppose this is our claim, this is the rough work. Suppose this is SR of X, this whole is SR of X, and then we have to prove that this SR of X is open set, and the definition of open set says that a subset U of metric space XD is said to be, and again suppose this is metric space, this is suppose metric space XD on which this SR of X is open sphere, and we have to prove that this open sphere is open set. Now suppose this is center X and this radius R, X and this radius R, and this is open sphere. Now we have to prove that this SR of X is open set. So we have to prove that for each and every another element in this open sphere, suppose Y is element of SR of X, and then we have to prove that there exists some radius greater than 0 such that the open sphere centered at Y with radius, some radius suppose S, must contain in this SR of X. That is, SR of X contains that open sphere. Don't confuse between contained in and contains. Since SR of X contains this S Y of, suppose S of Y and S of Y, this open sphere is contained in this SR of X. We have to prove that for every element of this SR of X, then we will take some Y is arbitrary element and prove that for that arbitrary element the open sphere centered at that element contained in SR of X. So after that we will say that this SR of X is open set. So our claim is SR of X is open set. So that is, we have to prove that for each, don't forget to write this, for each, suppose Y belongs to SR of X, R and X are already taken, so we will take Y. Suppose Y belongs to SR of X, then there exists some radius S greater than 0 such that this open sphere centered at Y with radius S, that is S of Y contained in SR of X. SR of X is said to be open sphere whenever for each Y belongs to that SR of X there must be some radius S greater than 0 such that the open sphere centered at Y with radius S must be contained in SR of X. We have to do this. Now here we have taken this Y belongs to SR of X. For each Y belongs to SR of X, we have to prove this. So now this is our main claim. We have to prove this. After that we will say that SR of X is open set. To prove this, we have this. Since this Y belongs to SR of X, since Y belongs to SR of X, so by definition of SR of X, definition of SR of X is any element belongs to SR of X, then distance between this center and that element must be less than radius. So if you take this Y belongs to SR of X, then the distance between X and Y is obviously less than R, because R is the maximum, so R is the radius of that open sphere. So this will give us distance between X and Y is strictly less than this R. Suppose this as equation number 1. This as equation number 1. Now we have to find the radius S. Radius S such that if we draw the open sphere centered at Y with that S, then that open sphere must be contained in SR of X. Now if we rearrange this equation, then we will get R minus of distance of XY. So subtracting distance of XY on both sides, we can write R minus of distance of XY r minus distance of xy, r minus distance of xy is greater than 0. Just writing it in opposite way. Suppose if we rearrange this equation, then we will get r is greater than distance of xy and r minus distance of xy must be greater than 0. Now we will choose this as radius s. It is clear that suppose now here you can see that, is it visible? Yes. Now you can see that this is radius r, this whole is radius r, and if we subtract this distance of xy, distance of this x and y from this whole r, the remaining will be this, and this r, if you take this r minus this distance of xy, this is the remaining distance, and if we take this distance is equals to x and draw the open sphere. Suppose I will take some another example. Suppose this is r, this whole is r, and suppose this is y. Then if we subtract this distance of xy from r, this whole is r, and if we subtract this distance, the remaining distance is this, and if we take that radius and draw the open sphere, then clearly that open sphere lie in s r of x. This whole open sphere lies inside this open sphere. So this r minus distance of xy is the best option, because if we take y is equals to here, then distance of xy, if we subtract this whole distance r, if we, this is r, and if we subtract r, sorry, distance of xy from r, then this is the remaining distance, and if we draw the open sphere, that big open sphere again lie inside this open sphere s r of x. So if we choose s is equal to distance of r minus distance of xy, which is greater than 0, then we can easily show that this open sphere lies inside that open sphere. Now we will take that s is equals to r minus distance of xy, which is greater than 0. Our claim is this s of y, this open sphere lies inside the open sphere s r of x. So to show that this s of y is contained in s r of x. S of y is contained in s r of x. So to prove that is we have to prove that this s of y is subset, proper subset of s r of x. We have to prove this is proper subset of s r of x, and we know that how to prove this. We have to take one arbitrary element of this set and to prove that element belongs to this. So we have to show that any element of this s of y, that is this open sphere, is again element of this s of y. The video got abandoned because of some technical issues. So we have to show that this s of y is totally contained in s r of x, and we know that how to prove this is subset of this another set. Let's take one element z belongs to this s of y, and we will prove this z again belongs to this set s r of x, and from that we can say that this set is subset of this set. Now let z belongs to s of y. So by definition of open sphere, we can prove that, we can write distance between this center and z is less than this radius, distance of y and z, or z and y is less than s. Suppose this as equation number 2. Now we will show this z belongs to s r of x. That is, we have to prove that z belongs to s r of x means we have to prove that distance between x and z is less than r. That is, we have to show that distance between x and z is less than r. Now we can use the triangle inequality, because xd is metric space and all those stuff is happening in the metric space, because xd is metric space on which we have taken some s r of x, and we have to prove some that this s r of x is open set. So this all these things happening in the metric space xd, so we can use the triangle inequality of xd. Now by triangle inequality, write the triangle word, whole triangle inequality. By using triangle inequality, we can write distance of x and z is less than or equals to distance between xy plus distance between y and z, but distance between y and z is strictly less than s, which is strictly less than distance of xy plus this distance of x and y is strictly less than s. So I can write it as this. Now this distance of xy plus distance plus this s. So I can write distance of xy as it is plus, we know that s is equals to, we have taken s is equals to r minus distance of xy. S is equals to r minus distance of xy. So we can substitute the value of s here and write distance of, sorry, r minus distance of xy plus r minus distance of xy. So minus of distance of xy and plus distance of xy will become 0. So the only r is the remaining term. So distance of x and z will be strictly less than this r. Distance of x and z is strictly less than r, and hence we can say that this z belongs to s r of x. Z belongs to s r of x. Thus, this z was the element of our s of y, and this z belongs to s r of x. So, we can say that this implies this s r of s of y is contained in s r of x. Hence, for any arbitrary element y, there exists s which is equals to r minus distance of xy, such that s of y is contained in s r of x. Hence, this s r of x is open set. Hence, the proof.